Botvinik-Nezer is currently a postdoctoral researcher at Dartmouth College. Her research interests include the link between beliefs, expectation, and physiology. She's the first author of a recent paper describing the collaboration of more than 200 researchers who analyze the same dataset. Her talk today will be the effect of analytical choices on fMRI findings. So, Rotem, please, the floor is yours.
Okay. Hello, everyone. I'm very happy to be here, and I will present the effect of analytical choices on fMRI findings in a recent study we published. And the main question that that this project was about is what happens when 70 independent groups of researchers analyze the same fMRI dataset. So we will go back to this question, but let's start with some background. So I'll give some background to the topic that led up to the project today. I'll start with the replication crisis, which is a name given to findings, recent findings that published scientific, scientific published findings are not as replicable as we might have expected. And it started with a large collaboration in psychology, with replicating 100 studies in psychology and demonstrating that only about 1/3 of the findings were replicable, with about half of the effect size on average. It went on with economics and biology, cancer, preclinical studies, and other fields that showed pretty much the same findings, not exactly the same proportions, but in general that we might have a problem with replicability. And there's an issue here about how you define a successful replication and what does it mean if one study is not being replicated in one other study. But in general, it showed that we have some problem that needs to be addressed in science in general, in many, many fields of science. And one reason that was suggested as leading to this was the researcher's degrees of freedom, which means that in many scientific fields, there are many analysis steps with multiple possible choices in each of those steps. And this may inflate the false positive findings rate and may also give rise to some questionable research practices, for example, p-hacking or hacking, or just trying to take your data and find a result that you can actually publish, even if it will not necessarily be replicable or reproducible. So in 2012, if we go back to neuroimaging, then in 2012, CARP published a paper where he did simulations with an fMRI dataset. He ran about 7,000 analysis workflows, and he quantified the variability in the resulting statistical max of each of those workflows. And he found that some of them were consistent, but others showed substantial variability. So the results sometimes were highly dependent on the specific analysis Python that was used, both in the activation, the strength of the activation, the location of the activation, and the extent of the activation. In 2018, Silverstein et al., they developed a many-analyst approach where they took one data set, a behavioral one in this case, and gave it to many different researchers to analyze it. So in this case, 29 analysis teams analyzed the same data set, and they tested the research question of whether soccer referees give more red cards to dark-skinned players. And again, they did a really good process there, and there were many steps, but in general, their findings show that the analysis results are highly dependent on the subjective analytic decisions, which are justifiable but different across researchers. So all this led to the thought that we might want to take a deeper look at how analytical choices affect our results. And one thing that was used in many of the replication projects was prediction markets. This came from the economics field. And on prediction, they were trying to develop a tool to predict which finding will be replicated or not, without actually running the study, because it's not always feasible to actually run the study, whether it's it costs a lot of money, or we need a lot of participants, or we can't, from other reasons, we can replicate a specific study. So what they do in prediction markets, researchers or peers from the field, they trade on scientific outcomes. There's like a stock market, and they receive money, and they put this money where they think, whether they think a specific study will replicate or not. And then the stock market is affected by all those choices. And at the end, the prices of each stock are supposed to predict whether a specific study or whether a specific result will be replicated or not. So this was used in many of the previous replication studies in psychology and economics and more. And All this led to NARPS, the Neuroimaging Analysis, Replication, and Prediction Study, which I'm presenting today. And this is the core team that was involved in NARPS. It started with the economics who brought the idea, and then the neuro people joined, and I joined afterwards. I will talk about it later. But this was the core team, but I will mention afterwards many other people that were involved in this project. Some of them are here, actually. And the aims of NARPS were two. The first one was to test the variability of fMRI data analysis and how it influences the results in practice, in real life, in an ecological manner. And the second one was to apply prediction markets to test whether researchers in the field can predict our results. And in general, what we did in the project, so first of all, we collected data, a new fMRI data set in our lab in Tel Aviv University. Then we distributed this data set to 70 analysis teams around the world to analyze this data. And we ran prediction markets to, again, to see whether researchers in the field can predict the results. So let's start with the data set. So the test that was chosen for this project was the mixed gamble test. It is usually used in the literature of, in the field of decision-making under risk. And in this test, on each trial, the participant is shown with a gamble or prospect with one number in green representing the potential gain amount he can gain, he or she, and on red, the potential loss amount. There's a fixed chance, 50-50 chance to either lose the loss amount or get the gain amount, and they need to decide whether they accept or reject strongly or weakly this gamble. At the end of the experiment, one trial is randomly selected and it is played for real. If they accepted the gamble, then they either choose either gain or lose this money. And we ran two different types of this task based on the literature. One is the equal indifference, where the potential gain is on average twice as large as the potential loss. And this is based on the loss aversion phenomenon, where people are more sensitive to losses than to gains, about twice the time more sensitive. And this was from the study of Tom et al. That was published in Science 2007. The other version was the equal range, where gains and losses came from the same range, so on average are the same. And this is from two other studies, from the Martino et al. And from Canessa et al. And it was used to address a debate on the literature and the findings, about the findings with this test. So the participants, sorry about that. The participants participate in this task, and we collect, while they were doing so, we scanned them with the MRI on Tel Aviv University. Here you can see the specific parameters that we use. Ronnie Vanier, a PhD student, master's student, sorry, from my previous lab in Tel Aviv, ran the study. And there were, at the end, after exclusion, there were 54 participants in each of the versions of the task. This dataset is published and openly available on OpenNeuro, and it was also published as a data descriptor in Scientific Data Journal last year, so you can all see it and have all the information you need about the dataset if you want to. We have two versions of this data. One is it is published, one is the raw data, and the other is a version that was pre-processed with fMRI prep. So the next, after we had the dataset, I joined this project, and the next step was to recruit an analysis team and distribute the data to them so they will be able to analyze it. And we recruited 70 teams. Overall, there were 180 members, up to 3 members per team. They came from 5 different continents and many countries around the world, and from different positions, PIs, postdocs, graduate students, and other. And they were all offered to be a collaborator on this project and to be co-authors on this project in return for their participation in analysis. They had up to 100 days to complete and to report their results from November 2018 to March 2019. This resulted in this long list of co-authors on the paper, which I'm proud to be part of. And I even needed to create code for this affiliation, which was great. So this was a community effort, and I think it represents a good aspect of our field, and I will talk about it a bit more afterwards. So thank you for all the people that are written on this slide. So after we had the data set and we had the teams, we instructed them to take this data set. So we tried to minimize the instructions. Okay, we want to test how analytical choices affect variability in the wild, in real life. So we tried to minimize the instruction. We gave them the access to the data set, both the raw data and the pre-processed version with fMRI prep. And we said, we ask you to freely analyze the data using your standard analysis techniques as you would for a paper in order to test the following 9 ex-ante hypotheses. And those are the hypotheses. I will not go too much into it because if you're not from the field, you might not be familiar with some of those aspects. But in general, there were 9 hypotheses. Each of them, you can see them all here. And each of them was related to either a positive or a negative activity in a specific brain region, the VMPFC, the ventral striatum, the amygdala, in relation to either the potential gain amount or the potential loss amount. For either one of the groups, if you remember, we had 2 different versions of the mixed Gamble test, so either the equal indifference group or the equal range group, or a comparison between the groups. For example, the first hypothesis is that the activity in the VMPFC will be more positive as gain increase for the equal indifference group. Okay, so those were the hypotheses, and we asked them to take the data set and test those hypotheses. Then we asked them to report at the end of the analysis, report a binary decision for each hypothesis based on an all brain corrected analysis and not a small volume correction or anything else, to report their methods. And in order to have as many details as possible, we used the COBITAS guidelines that were created were published in 2017, and we created a form based on them, a very long one with 11 pages, and they needed to report almost every aspect of their analysis. And we asked them to create a new collection on Rovereto and upload 1 thresholded and 1 unthresholded statistical net to this collection. 1 for each hypothesis, of course, on which they based their decision. So let's go back to the initial question. What happens when 70 independent groups of people, researchers, analyze the same fMRI data sets? So first of all, the variability of the analytical choices was very large, and it was demonstrated by the fact that no 2 teams chose the exact same analysis pipeline. So 70 independent teams and 70 different analysis pipelines. The teams made different analytical choices at different stages of the analysis. For example, what software they used, what pre-processing step they included, and what parameters they used in each of them, how they modeled the hypotheses, with respect to the regressors and the contrast they use, what method they use to threshold their data, correct for multiple comparison, how they define the region of interest, and many more other steps. So 70 teams, and they use different methods, but the question is, did their results differ, right? And so here are the main results of our study. And shortly we can say that the answer is yes, but let's look at the details. So you can see here a plot of the percentage of team reporting a significant result for each of the 9 hypotheses. So the hypothesis number is on the y-axis, and the percentage of team reporting significant result is on the x-axis. And remember that 50% is the maximum possible disagreement across teams, while 0% means complete agreement on a non-significant result, and 100% means complete agreement on a significant result. On the ER and EI means equal indifference and equal range. So whether it's for the equal indifference group or the equal range group or the difference between them. And here you can see whether it's a positive or negative hypothesis. This is whether the hypothesis was about positive or negative activity, which region, and whether it's related to the loss or to the gain amount. So let's start with hypothesis 5. Here you can see it. 84% of teams reported significant results. So in general, there was agreement that it was supported by the data. And hypotheses 7, 8, and 9 were supported by only 6% of the teams reported significant results. So there was a general agreement that they were not supported by the data. But if we look at the other 5 hypotheses, 1, 2, 3, 4, and 6, you can see that the agreement was not as large. And on average, about between 20 and 40% of the teams reported a significant result on those hypotheses, and it seems that they were highly dependent on the specific pipeline that was used. So overall, for most hypotheses, we found considerable variability across teams, even though they analyzed the same data to assess the same predefined hypothesis. So let's try to look at the sources of the variability. What caused this variability? So Wasp Poldark was in charge of this analysis, and you can find a fully reproducible code of all the analysis that we'll talk about now of the team's data on these links with the container and everything. So let's look at the details. First, we tested what parameters of the analysis pattern were related to more or less significant reported results. So we performed a logistic regression with the sum of the analytical choices that we could include in the model. And the outcome variable was whether each team reported a significant or non-significant result. And what we found was that, first of all, the estimated spatial smoothness, this is not the factor they use for smoothness, but the estimated spatial smoothness from the maps with FSL smoothness function, it was significantly related to reporting more significant results, so more smooth equals to more significant results. The second thing was the software that we use for analysis. Teams that used FSL tended to have more significant results than teams that used SPM. And the thresholding method was also significant. So teams using a parametric thresholding method were reporting more significant results than teams using non-parametric thresholding methods. Whether the team used or the fMRI prep pre-supported data. If you remember, we gave them raw data and also a version pre-processed with fMRI prep. Some of them, about half of them used it, about half of them did not. And using or not using this was not related significantly to reporting or not reporting a significant result. Also, modeling head movement or not was not significant. But I want to emphasize that there were many other analytical choices that we couldn't actually test here. For example, how they define the region or which regressor they put in the model. And the reason for this was that there were just too many options that the teams used and we couldn't model it. We didn't have enough power to include it in our model. Although we had 70 teams, it was still not enough for this. Also, we ran a non-parametric bootstrap analysis to confirm our results, and we found a consistent, and we found support for our estimated spatial smoothness, but inconsistent results for the other two findings. So the next step was to look at the level of thresholded maps. Is the variability also present at this level? And you can see here the overlap across teams for hypotheses 1 and 3. They share the same map because they differ with regard to the region, but there are the same hypotheses besides this. So the unthresholded map, the thresholded map and the unthresholded map are the same. And you can see in colors voxels that were activated in the thresholded maps for at least 10% of the teams, with the color representing the percent of teams for which the voxel was active. Red is high and green is low. And overall, the agreement across teams was largely limited to the voxels that were not active in all teams. But the location and the number of active voxels considerably varied across teams for every hypothesis, from 0 active voxels to tens of thousands of active voxels. So the variability was considerable even the thresholded maps level. Then we proceeded to look at the level of unthresholded maps. And surprisingly, at this level, we found relatively high correlations between the maps of most teams. So you can see our correlation metrics with the Spearman correlation for each pair of team. This matrix is clustered to 3 clusters using word clustering on Euclidean distances. And you can clearly see 3 different clusters. One, the purple, consisted of most teams with high correlations in red. And you can see the mean, however, even in this cluster of many teams with highly correlated results, if you look at the colors here in the columns here, so red represents a team reporting a non-significant result, and green is for teams reporting a significant result. And you can see that even in this cluster, they reported different results. So the variability was still large in the reported results. Another thing you can see here is that one of the cluster here is in blue. So it is anti-correlated with the other teams. And for these 7 teams, we looked into their design matrices and we found some modeling issues and misspecifications that I will not elaborate on now, but you can see at the paper. This pattern was similar across hypotheses. Not always you see the blue one because it depends on specific things, but you see one cluster, a big cluster with high correlated teams, and on general, the maps are very red, and you can see that there was high correlations between teams and the other unthresholded maps. But nonetheless, so we have correlated unthresholded maps, and we have different binary results, right? Even for the main cluster. So this suggested that the final steps from unthresholded maps to reported results, including the thresholding, correcting for multiple comparisons, and region specification, are the main sources of the variability. So we wanted to look into this. And what we did, we applied 2 different consistent thresholding methods and consistent ROI region of interest specification to the team's unthresholded maps. So we took the unthresholded maps of the teams, we applied the same thresholding methods, the same ROI maps, and we still found that the results were highly variable. So it was different, of course, and it's more complicated than this, but qualitatively, the variability was similar in results even after we did this. Finally, so this suggests that this is not the only source of the variability. So it's not enough to just find a solution for the final steps. Some of the variability also comes from the steps before the unthresholded maps. So finally, we performed an image-based meta-analysis or a consensus analysis on the unthresholded maps of the teams. We found significant active voxels for all but one hypothesis, and we found confirmatory evidence for 4 of the 9 hypotheses. And overall, the meta-analysis on the unthresholded maps revealed convergence across teams and seems like a promising solution for the future. Now let's go to aim 2 that we talked about, to apply prediction markets to see whether researchers in the field could predict our results in this study. So we ran 2 different prediction markets. The first one was for researchers from the field who did not participate in the analysis part. 65 active traders participated in this prediction market, traded in this prediction market. And the second one was for analysis team members. 83 team members participated, and again, so this is people that were part of the analysis, but they then participated in the prediction markets. Importantly, the markets were run after all teams submitted their results, but the results were kept confidential. So during the prediction market, analysis team members knew their own results, but not the results of the other teams. And I just want to remind you, so prediction markets, so the traders participate in some kind of a stock market about each of the hypotheses, and they take the money they got and put it in on each stock, indicating whether they think it will be. It was about what would be the percentage of team reporting a significant result for each hypothesis, and the final prices of the prediction market are supposed to represent the prediction of the market. So let's look at the results. In pink, you can in the y-axis you can see the final market prices, or the proportion of teams reporting a significant result, either for real or the predicted one. And on the x-axis you can see the hypothesis number. Note that this is not from 1 to 9 here, but based on the proportions. In pink, this is the actual fraction of team reporting a significant result. In green, you can see the non-teams members prediction market beliefs for each hypothesis, and in blue, the predictions of the team members. So one thing that is obvious from here is that they consistently predicted a higher percentage of teams reporting a significant result than the actual fraction. So they were over-optimistic. They thought that the result would be more replicated than they actually were. And amazingly, even if they participated themselves, so even team members that themselves rejected the hypothesis, they still predicted higher support on the hypothesis. Another interesting finding was that the traders in the team members market in the blue were highly calibrated. So they consistently predicted higher proportions, but their predictions were highly correlated to the actual results, 0.96 fMRI correlation. You can see here, the blue and the pink have very similar pattern. Another interesting finding was, so each participant in the prediction market self-rated their expertise in neuroimaging and their expertise in decision sciences. And those self-rated expertise were not significantly related to better prediction. So people who are more expert, or at least see themselves as more experts, were not better in predicting our results, or to the other way. So to summarize, we gave 70 independent teams of researchers from around the world the same fMRI dataset, and we asked them to test the same 9 hypotheses. And we found there was substantial variability in the analysis pipelines they used, leading to substantial variability in binary reported results. And although the unthresholded maps were relatively correlated across most of the teams. And we also found that there is a convergence across teams in an image-based meta-analysis where we took into account the correlation, the dependency between teams, because this was the same data. And we also found with prediction markets, we found that there is an optimistic bias in the field. regarding the replicability and reproducibility of results. So researchers in the field consistently predicted higher proportion of significant results than we actually saw in the actual results. And there are many aspects to this project which we can discuss, but I think one point that is important to emphasize is that 180 people are authors on this paper, because this was a community-wide effort to self-examine the field and to improve and to find solutions and to see how we can make our field better and more producible and to make our findings more reliable. And I personally was amazed by how many people were willing to put a lot of effort and so many hours into this project. And I was very lucky to collaborate with all of them. And another point, important point to discuss here is that our results show that it's really important to share data and share code, and you're talking about those kind of stuff in this workshop. And I think it's really important because the final results are one thing, but the things leading to this are really important. So we need to be sure to make sure to provide detailed methods on our papers and to share the data and to share the code so people will be able to see what we did, and if needed to test whether our results are dependent on the specific things we did or not. And pre-registration is also an important aspect here because it will help avoid the possibility of p-hacking, intentional or unintentional p-hacking, and trying to get a result, because our results actually show that for all the 9 hypotheses, you can find at least 4 different pipelines that led to significant results for each finding, even like for the 3 that were almost not supported by any team. So it means that if you really want to find a significant result supporting your hypothesis, there's a good chance you can. And we need to find ways to avoid this because of the publication bias. Our main suggestion how to improve is the multiverse analysis, which means that each study, we believe, should be, each dataset should be analyzed with many analysis pipelines that are justifiable and make sense and reliable, and then look for the convergence across those analysis pipelines. So one analysis pipeline is not enough because it will not necessarily provide reliable results, and we're interested in the results that are shared across pipelines that are consistent and are not dependent on specific analytical choice. Another point that is important to emphasize here, that in this study we didn't have a ground truth, so we don't know for each hypothesis whether the truth is that it should be supported or not, it should be significant or not. We don't know if the activity in a specific region is really related or not, but we use the test that is frequently used in the literature, and there was a debate in the published literature about it. And what's important here is that our findings in the field are dependent on analysis pipelines, and not whether a specific pipeline, here at least, not whether a specific pipeline is correct or not. I believe that there is no one analysis pipeline that is optimal for everything, and anyway, it depends on the specific study, the data set, the specific hypothesis. And so I don't believe we need to try to find, I think we should verify our pipelines, but I don't think we can find one optimal one. And I think we should do the multiverse analysis and try to run many reasonable and validated pipelines and find their convergence, like I said. This specific task we could have chosen a different task or different hypothesis, and maybe we would get different results, and this can be tested, but this is a pretty common task to use and pretty representative, I would say, task in the field. So, for example, we had the VMPFC, which is a region with not all groups would define it the same, because it's more functional defined than structural. And maybe if we didn't choose this region, we would have different results, but I think it represents, those hypotheses in this test represents the field, and it may generalize to other tests and hypotheses. And an important aspect of here is we believe that this is important far behind fMRI. So every field with multiple analysis choices and complex pipelines and multi-dimensional data would probably suffer from the same problem. They showed it in PET, and they kind of showed in preliminary stuff in diffusion data, and they're thinking about doing it in EEG. And I believe that many scientific fields nowadays have so much data and so many somewhat subjective analysis choices to make that it will probably show the same patterns. Like like it happened with the replicability projects. So we believe that other fields should also look into themselves, and here that we have the opportunity to improve our field and make sure our findings are reproducible. And I want to thank everyone that was part of the project, mainly Tom Schomburg, which was my PI, my mentor during my PhD in Tel Aviv University. I'm now a postdoc at Dartmouth, but I moved recently. And Russ Poldrack from Stanford University, who also led this project, and all the NARPS team, all 196 co-authors of mine, and mainly the 180 analysis team members who really made the difference for this project, and all the people participating in prediction market. And of course, the funding agencies, there were many, but the three main ones were the Austrian Science Foundation, the Israeli Science Foundation, and the Jane Volunteer and Rotem Botvinik-Nezer Foundation. And thank you very much for listening.
I'm curious about whether people use the raw data or fMRI prep data, because my hidden question would be whether fMRI prep, tomorrow we will have Oscar Esteban talking about fMRI prep. So I was wondering whether we could start to consider fMRI prep data as like the new standard, let's say, for starting an analysis.
Yes. So in this project, about half of the teams used the pre-post data and half did not. I would say that it doesn't necessarily represent like the 50% of the field uses fMRI prep or not. First of all, some teams ran fMRI prep but did not use the version that we provided.
Okay.
This was one interesting, but again, not many. So at least at the end, about half of them used fMRI prep. And the reason we provided this data was that because we know that analyzing 108 participants requires significant resources, computational resources, and we wanted to help teams that were maybe at difficulties doing this, so to help them and provide this data. And we were kind of lucky that half of them use it and half not, because then we could actually test the effect of this. I
would have another question as well. I used to call these data sets something like, this is not a collection of data, it's a properly described data set because it's in the BIDS or BIDS format. So I would ask you whether, I think you started collecting data in 2017 or stuff like this. So did you, this is let's say a technical question. So whether you started collecting the data having in mind that you wanted to arrange that in BIDS format just from the start. Because I think this is also, in my opinion, this was like a game changer for making all those people analyzing the data. Without the BIDS format, it would have been like impossible to approach a data set which is that rich. Yes. So I agree. I would just emphasize again that I didn't collect the data. It was in my lab, but it wasn't by me. It was in July 2017. And yes, they knew they were about to share this data with many teams, and we knew that the BIDS, actually in my lab, we used BIDS anyway this year in this time, so, and still are. So it was kind of obvious for us, and Russ Poldrack, who is part of BIDS, was also part of this project. But yeah, I agree that using BIDS was a great thing to do, because it enabled many teams that are trained with using big data to participate in 200 tools. So, although also we could run fMRI prep based on this quite easily, and we also ran the MRI QC and provided some quality and control measurements to teams. So yes, I agree that it was important, and yes, it was on purpose. Okay, there is actually a question I would bring on screen. Paolo Esani, which I mentioned before.
Thanks. First of all, thanks for your wonderful work, and I believe it's really helpful for all the community. And I have a question on how this effort can be helpful for education. Recently, I believe it's very useful to propose to the student to replicate published work as a kind of training. And in this case, this experience of replication might be disoriented for the student, because might be very difficult to exactly replicate for so many details. You cannot really follow the original work. And so how do you believe your work can be helpful for, let's say, educational purpose?
First of all, accuracy is very important to train people and to show them what happens when you try to replicate. I think one problem in neuroimaging is that actually replicating a study is quite expensive. And this is one of the reasons in this project we used one data set and provided to many teams and not tried like they did in psychology to replicate many different studies, because it would be very expensive to try to replicate like 100 neuroimaging studies, of course. And I think one thing that one can do to train people is to take published data sets and let them analyze them and see if they get the same results. It would be great if they could reproduce the results exactly with the same pipeline, but for this they need a paper that made a good job describing the methods. And I think this is one thing that many people now are trying to improve. So the COBITAS guidance, for example, that I presented before, Remy Gao and some other people are trying to create now apps that can actually help you report all your methods and all those details more easily. And then it might be easier to reproduce results. I think now it's kind of hard to ask a new person to replicate finding in MRI. But again, I think using, like we did, so using a published data set and trying to reanalyze it is a good practice, and you can learn a lot both about the analysis, which is important, about the field that is important, and about replicability and reproducibility, and how beneficial it is to have open data and how important it is to report your methods. Another aspect of the study that may be relevant to training, Jeanette Mumford talked about it on OHBM, is that I told you that we found 7 teams with anti-correlated results in the amplitude maps. And when we looked at the design matrices, and we were lucky to have the design matrices here, because usually no one actually published their design matrices usually, right? We're not supposed to, or we're not asked to, at least. So by looking at it, they found a specific misspecification that happened, and they could realize what happened there. And I think also there's an opportunity to train people on how to define their model correctly and make sure that their question and their model are in line, and they can actually, that the results actually mean what they think they are, which I think is also an aspect that we saw here. But I didn't talk about it much during the presentation. Again, if someone wants to hear more about it, then Jeanette Mumford, presentation on OHBM is relevant.
So you show us that using a different tool brings a different result or introduce a bias. So from certain point of view, we may consider to converge to, let's say, a kind of a best tool, or to use the same tool in order to lower the variance in the result. But from the other side, we may miss that to understand what is the bias specific or let's say the best tool we converge on. So what do you believe about this trade-off between having variance related to the tools and having just one tool but with unknown bias?
Thanks, it's a great question. So I briefly mentioned this during the discussion part, but I believe that there is no one optimal tool, and that if we have different hypotheses, different data sets, and so different tools will be optimal. So this is why I think we shouldn't try to find the best one, but rather to find, I don't know, some thousands of or hundreds of good pipelines, and find a way, develop methods to run many different analysis pipelines, just validated and verified analysis pipelines, and find a convergence across them, like we did here in the meta-analysis. So I think we should, I don't think we will, the field will never agree on one data set, on one analysis pipeline, and I don't think we even should. Again, I think that the multiverse analysis, where you run multiple pipelines and look for the convergence, is the best thing, because we want the results that are not dependent on a specific pipeline.
So I'll bring on screen Guilmar.
Hi. Yeah, thank you very much, Rotem.
Thanks.
Yeah, it's an amazing work. I was so impressed that I was trying to convince the MEGT community to try to do something similar there, but there were some people a bit skeptical about, because in the MEG field maybe we don't have such as standardized pipelines to analyze. I wanted to ask you if it was in the case you did, people use custom-made scripts, or do they use like some more standardized workflows?
Okay, so thank you. This is, yeah. So first of all, I would say that I know that in EEG they're planning to do something, so maybe it's close enough. And if you say that there are no like agreed upon pipelines, standardized pipelines, that even I would predict that maybe your results will even be more dependent on the specific pipelines. But even here, like we have a standard pipeline, we don't really have one, right? Because 70 teams is 70 different ones. And with regard to your question, so there were many different choices that teams made. Some used SPM or FSL or AFNI, some use custom scripts, some used a combination of the software and custom scripts. So we have a table, a huge table with all the methods they used and they reported, which is publicly shared with the code. And I think there are like just all the options were used. So like there wasn't one. There's not like most of the teams use a specific Python on FSR or something like this. We were far from this. They use very different pipelines, and many teams had custom scripts in different stages of the analysis also. So some use one software for pre-processing and another one for analysis and etc.
Okay, then I think then maybe the most difficult part is to come up with an experimental data set or some clear hypothesis of what to test, right?
Yeah, I agree. I'm saying I wasn't part of the decision about the specific test and hypothesis because I only joined after the data set was already collected, but I agree that this decision was important and I do think it represents the field. But I think even if other hypotheses were chosen or a different tests, maybe a different software would affect the results differently. But still, I think the main message here is that the analysis choices we make change our conclusions. And this is important. And we need to think what we should do about it. And I think we should find a way, like I said, like the multiverse analysis, find ways to have results that are not biased based on the analysis pipeline for the specific researcher. Does this answer your question?
Yeah, thank you very much. Maybe I will write you an email and ask you a bit some more details in order to extend this and try to convince the MEG community. Thank you.
Thank you very much.
Thank you.
So would you think that this could be, so there are actually two questions. The first one is whether this could be also like a result, let's say, a combined effort, like a multi-center effort. For example, if, for example, someone doesn't have really the possibility to scan like 108 participants for just one project, so spread the acquisition throughout the centers could be feasible. And the second part, which is kind of connected, whether this could be like a bottom-up process, or it should be like something that you decide and start and go from there to the acquisition. So I'm just asking whether people have like, for example, resting state data in the drawer, and for example, MEG resting state data in the drawer, and they could just put together all the efforts from many centers and try to build an initiative like this.
So just to clarify, your second point was more about the analysis, and the first one was more about the acquisition, right?
No, my second point, sorry if it was not clear, I was just wondering whether this could be, you can replicate an initiative like yours, having already collected the data and just selecting, for example, all the resting state data with collected on Prisma with 100 milliseconds with 1 second TR, that resolution, and so on, put together, throw on the table a few hypotheses and try to replicate what you did?
First of all, yes, I think it can be done and it can be very interesting. And I think you started with trying to take a data set that was like the acquisition was in different centers, right? Like not only one center. So I think it's very interesting. The reason it was not relevant here was that we try to show what happens in the real literature. So currently it's quite rare to actually have a data set that was collected in different centers. It's starting to be more common now. But if we look at the published literature, most of it is dependent on a specific data set that was collected in a specific center. So this is why this was more relevant here. I think it will be very interesting to see how the acquisition in different center affects this result and whether people analyzing the data set that was collected in their center versus not their center, and maybe they're less used to it, and maybe the pipeline is more their pipeline is more is optimal or better for their the data that comes from their acquisitions and stuff like this. It will be very interesting. And yes, I missed some of your questions probably, sorry. But
no, I think
again,
it's fine.
I think it will be very interesting to try to test this. And the important thing is try to think how those projects can help us improve. So you asked whether it should be bottom up or top down, right? So I think that most changes need both, probably. But here we have almost 200 people from the field thinking that we should change something and knowing and having a suggestion. And I think here we mostly need the tools to change. So if we say we want to run multiple pipelines and see the convergence, we need the computational power and the tool to do it. So people are already working on it, and once we have it, I think it will be easier to see the change coming bottom up because people will be able to actually do it and not just say they should, right?
Yeah, it's a very good comment.
Yeah, and another point is that if I'm going back to the CARP study that I presented from 2012, so he took one data set and ran simulations himself. So we didn't use 70 different teams, but just ran all the pipelines he could think of. And I think it's also interesting because, again, if you want to validate pipelines, you can use this. You can either take many data sets or simulate data sets and try to see what happens in each analysis pipeline. But here we try to see what happens in real life. So we wanted to see what actual researchers in the field are using and how it affects the results. So this was the difference here. But if we want to validate pipelines, we can also do it with simulation studies or with just like single lab running many pipelines on the same data set.
Thanks again, Rotem.
Thank you very much. Thank you very much for inviting me. Thanks for listening. Bye-bye.